So let's start. What I mean about adaptation? Well, the first thing I want to say it is the following: why neuroscientific approach and not engineering? Well, this is my kid. Is right now 11 months, but I've seen developing for 11 months, and I can tell you that this is magic. What they and not it is not only about dexterity, it is about the learning itself. It is one-shot learning. It's amazing. It's adaptation. It's everything, right? So we are so far away from this type of skills from human that we really need to take a look very close to what is going on in the brain. And the second motivation that I wanted to show it from this approach is a little bit more in the engineering side, right? Is a little bit intuitive. I call it the Jupiter experiment. And in simulation, the Jupiter experiment will be just that I change the gravity parameter to 24.79 meters per square second. Sorry. So what happens if I have a robot with a controller tuned in the Earth and I just move it to Jupiter, just one parameter? I will put what is going to happen, and then you will start to have this undesired behavior. And of course, if you are a human and you go to Jupiter, you will also struggle, but suddenly you are adapting, right? How we can actually put this type of adaptation into robots. And more interestingly, if we can put adaptation, but also we can keep the precision that we have in robotics. So we have the side of the humans of adaptation, but also we have the amazing part of precision. And in this rationale, for me, if you have this adaptation with uncertain resolution, you will have safety. And this is the main goal of having adaptation in robotics, apart from generalizing to different environments. So what is the difference between adaptation and learning? There is not so much difference. I always like to put this paper from Kenji Doya, that is talking about the specialization by learning in the brain, where he identifies different regions of the brain with different types of learning, right? If you can think about it, the cerebellum would be kind of supervised learning, basal ganglia reinforcement learning, and cerebral cortex unsupervised learning. But this is type of learning. But when I was trying to understand what is going on in the brain, one option, and also this is, of course, an hypothesis, is that you can think not only in learning types, but also prediction types. You can think that actually the brain developed to be able to predict in different scales. If you go to the cerebellum, it's a very fast scale of prediction, and then you go to the cortex, and we are having a very specialized prediction in a bigger scale. So in this sense, prediction, and that's why I call it adaptation by prediction, is a core mechanism for adaptation. And prediction, we can do it by learning, okay? This is a very classical from 1994 problem, but still in motor control, they still use it. I love it. You just ask a participant to move like a robot in different direction that you see here in the dots. I don't know if you can see my cursor, but you have different positions that you can move. And then you just track the trajectories, and then you will have this type of profile. But if you apply a force field in the robot, so you can modify the behavior of the environment, you will get the following. You will get in several training test steps, you will have the first, you will have a very fast adaptation of what is going on, that is A, and suddenly you are converting to the original kind of optimal trajectory, okay? So you have like different type of adaptation here. The adaptation that is very fast, that's the one that I'm going to focus today. And then you have this adaptation by learning, okay? Good. So another important aspect that I wanted to convey to you is we did an experiment because we were seeing that the people in virtual reality, when they put in the goggles and they saw their body, what they were doing is what we call it the avatar follower effect. They were correcting their body in order to fit the visual input. Okay, this is a slightly a small effect that you can test it, and we did an experiment. What we did, we put a VR goggles, and then we modified what they can see in the virtual scene, and actually we put it 3 conditions: the hand on the left, the hand on the center, in the same position, on the hand on the right. What we observed, and this is the crucial point that I wanted to convey, is that the participants, because we were recording the forces applied here, were exerting kind of forces to correct for this discrepancy in the visual input. So it is not only to correct, so we are not only putting actions, okay, controlling, adapting to the environment when the environment changes, like in these force fields, but also when we have multisensory conflicts that actually are conflicts to our models, we try to correct. And this is also a very fast local adaptation, okay? I hope that with this motivational side, I convince you that this is important to model this into robots. And this type of adaptation is a very fast adaptation, very local. And what I told you is like there are different learning mechanisms strongly related to predicting input at different timescales. Also, you can think about reinforcement learning in the same way. We have also, as I said, de novo learning. So this type of I learn a new skill versus motor adaptation, that you are on the fly having various fast timescales, okay? And then the last point that I made is like we have multisensory and environmental conflicts that we, assuming that we have a model, of course, of the world, that is also controversial, but what we do is to correct by means of unconscious actions. This is a very fast adaptation mechanism. Good. So how we can model this into robotics? And in the last 5 years, we did some experiments into the robots, in the humans especially. And the idea is very simple. If you have a world model of the body and the world, what you can do is to try to approximate what you think about the world to the real world. In probabilistic terms, you will try to approximate your estimation of the world, your distribution of the world that is internal, to the real posterior, what is going on. And this approximation, that is this trying to fit my model to the world, will be the consequence of this adaptation, okay? I will show you an example with the ICAP robot that it was done by one student, by Guillermo Oliver. What we tell the robot is to maintain the hand in the same position, no? And this yellow thing will be the end effector. So then what we are going to do is to change the end effector position. We don't change anything in the algorithm, okay? It is just approximating my model to the posterior. So what is going to happen, and you will see here, is that the robot will perform some movements in order to correct for this. Let's see if the video works. Yes. So here you see that the experimenter, Guillermo in this case, is removing the end effector, and the robot is trying to do its best. That is, actually, I don't know anything about the world, so I just try to fit my model. And if you think in a human, it's like if you extend your finger, or if you just shorten your hand, right? So you're trying to stay there, but here, what I'm saying is that there is no learning involved. I mean, you have learned the model of the world and the body, but then it's just an approximation, adaptation, just trying to approximate these two distributions, okay? So I will not go super deep into the model. If you are, if you like this type of approach, just please look to the papers that we have, especially the survey that we have. But the basic idea is that you have a body state that is you cannot observe, so you have to infer. And then you have observed variables that are the sensors and also the actions. And then this approximation is very easy to do with something that in machine learning we usually do, that is the Cantilever divergence, okay? The KL divergence. Particularly, we use, to make it tractable, we approximate the variational free energy bound of the elbow. And this is very interesting because in the end, and I'm trying always to put this idea that actually is very normal and very used in machine learning and robotics. That is that you have here, when you have the variational free energy bound, here what you're approximating is to the generative model of the world. Okay, so you have the generative model of the robot, and then you have the generative model of the world. And this actually helps a lot, but not only for perception, but also for action. Good. In our approach, and this is called the active inference approach, we can use this quantity to compute everything. So we are trying to release to just one quantity all computations, state estimation, control, and something very important that maybe it has been talked in the workshop, that is a precision, that is how you, what is the relevance of the signals that will be so-called attention. Okay, good. This is just an advertisement. Just in case you're interested in this type of approaches, you can. We have every year we have an international workshop, but this time will be a conference already. Please take a look if you like these approaches, and please join the community. Good. That was a advertisement. So in the end, what we do is we were going to do adaptation through optimization, but then we go one step further. Instead of optimizing in any way, what we are going to transform the optimization problem is into a differential equations that traverse the variational free energy bound. Okay. The cool thing of this, I mean, you can do also in discrete, but the cool thing of this is that we have here a continuous form of continuous estimation and continuous control, in the same form that you will have a Kalman filter or you have a LQR control. This is the simplification of the formulas, more or less. And the important thing here, the important point here, is that in the end, you are having some differential equations that are making the system to go down the hill to optimize the free energy bound. Okay, good. If you have that, then you have, know that the adaptation is all the time working here, but in this specific case, we put some preference on the posterior distributions, right? So we want, so the system has some intentions that is modeled as the goal distribution. And then you can have this type of very fancy behaviors, like it looks like a kid, but in the background, you are always running this adaptation mechanism, okay? Know that this behavior that is looks like goal directed is very local. Okay, so it cannot be very fancy planning. It is just reactive, okay? Or reactive to minimize the free energy bound, okay? Good. The cool thing of this type of modeling with the functionality is that we can have multimodal estimation. In this case, I did it with the low dimensional input using Gaussian processes. And you can put, for instance, tactile stimulation for estimation. What else we can do? We can scale up. So we have low dimensional that you have seen before, but then we can just parameterize the distribution with a general function approximators. And if you play with the math, in the end, this is very easy using neural networks, okay? And what you can get is, for instance, pixel-based estimation of the body that you can see on the left with the now robot. This is already can be done with many algorithms, but the interesting here is that it's just a very local fast adaptation mechanism that is actually doing this estimation. And also we can do action. In the action, I have to say that has a local minima in this case because of the visual input. So you cannot do it for planning long sequence, okay? So we can think about the planning as another layer on the top of this adaptation mechanism. Good. We can even go further and having multimodal, but also high dimensional inputs of all, and then you pack in the latent space, as is the common thing doing right now in robotics, in a Z space, all the information compact. And then you can have, again, estimation and control. In this case, I want to focus on one specific thing that we use torque control, and I want to show you what is going to happen when we inject noise, and also with the gravity, with the Jupiter experiment. In this experiment, what we have is a panda robot in simulation, and we have different goals in the visual field, and we want that the robot just track this. Okay, so this just have to arrive there. And we're comparing our multimodal active inference, one that is not multimodal, and a standard optimal control with the Panda robot. Hopefully works the video. Yes. So in the left is our algorithm. On the right, it is the standard controller. Of course, you can improve it, but our controller is natively prepared to adapt to this noise injection. Okay. The same happens with the Jupyter experiment. With the blue is the normal controller. And then you can see that there are some problems, strong problems from 10 to 12 seconds. And this, in this case, the multimodal also plays a role. It is not only about the algorithm adaptation, but also how you integrate the information. Good. I think I'm good in time. I don't know what the time is at, but hopefully, yes. The last message that I wanted to convey with this high dimensional adaptation is that also you can adapt to internal or external changes. For instance, inertial changes, we put it a bottle with water on the effector, or we put an elastic band. And here, the interesting thing is like this algorithm actually adapts. But in the beginning, I thought, okay, adaptation means that you are less precise, but this is not exactly true. There are many cases that even when you have adaptation, you can even be more precise than standard algorithms like model predictive control or impedance control. Okay. Of course, this is not totally fair because these algorithms are not super tuned to this particular example. So the last thing, I said that you can approximate your internal distribution to the world distribution functionally, right? So we have some differential equations, but you can also learn to do this. And this is how I want to end, because that's why I said adaptation by prediction. If we have, and this is a very naive example, auto example performed by my PhD student, it was like, we tried to do this the same, but to learn it, instead of doing the function approximation and minimizing the free energy, we wanted to actually learn to adapt, right? So we are going to train the policy network by backpropagating through the prediction network, okay? And you can see here on the right, this is the arm that we are training to reach this moving object. And this is the variables that are being predicted by the transition network. And if you plot what I told you in the motivational example in the beginning, in the iteration 20, you try to adapt, and then in iteration 150, you start to be more precise. And I put it here also the LQR control, so you can see that we actually don't think that we have exactly LQR control in when we move our body. We are more closer to this adaptation plus learning scheme that we have in the brain, okay? So take-home message from my presentation, and hopefully it was clear. The first thing is like humans have flexible body estimation and control that in some sense functionally minimize the prediction error between the model that has been learned from experience and reality. And we really think that robots mimicking this property will be adaptive to model situations. In this case, adaptive in a very local, fast perturbation scheme, but you can also scale this with another layer of learning. The second point is that this type of neuroscience-inspired generative models are actually internal generation action plans, okay, that are conditions or learned from preference. Preference will be what you want to achieve. And importantly, they didn't get into the details of the computational model, that these signals, this prediction error minimization is modulated by precision. Precision is how relevant is a signal error into the estimation of your world, okay, or into performing an action. And we see a lot of strong potential for robotic applications, and we have examples with drones, navigation, with automations, and we are now moving also to exoskeletons. So this is my end slide. I just moved to Madrid to open my new lab. I'm hiring people with this type of approach, if you liked what I said, and you are, or you know anybody that's looking for postdoc or working in this type of mix between neuroscience and robotics, please contact me. Thank you very much.